Hello everyone. Today we are writing a sequence-to-sequence translation model with attention using Pytorch RNNs from scratch. We are doing French to English today, but it basically works between any two languages. I will cover a lot about the algorithms behind sequence-to-sequence models and the attention, as well as how to prepare the data for training and the techniques to maximize the computational efficiency and model performance with batch training. Before we get into anything technical, I want to show you this first. These attention graphs are taken from the attention layer of our decoder that we are later going to write. The x-axis is the French source sentence, and the y-axis is the English sentence translated by our model. All these test sentences are never used for training. They demonstrate that our model actually has built interpretation for the sentence meanings with the attention mechanism. So let's get started. And first thing first, I will show you the dataset I'm using. So I found this Pytorch website. This is also an introduction to sequence-to-sequence with RNNs, but my algorithm is very different from theirs. However, I found this site really useful for us to understand these similar algorithms. And yeah, you can go through it. And they have some nice diagrams to show the relationships, show you the structures. And the dataset I'm using is actually here. You can click this to download. And I will put this link under my video. So we can check out the downloaded dataset. It's like this. Yeah, so in this data file, it's actually two columns separated by tabs. And the first column is English, the second one is French. And this is ordered actually by the length of English sentences, and it's actually large. It has over 100,000 lines, and we're not gonna use all of them. Let's go through a brief introduction of our model. Let's put attention aside for a minute. Showing in this screen is our encoder. This is actually very straightforward. It's just an RNN which can directly be constructed using Pytorch's RNN class, or definitely GRU or LSTM. Here we give it an initial hidden state to start, which are typically zeros because there is not yet any information. And the inputs here are what's called word embeddings. The basic idea is that you represent a word with a bunch of numbers. Typically, the number of numbers range between 100 and 300. And these are actually trained parameters, and we won't be using pre-trained embeddings today. The way to handle this is basically you create a vocabulary for each language that assigns each word a unique integer index, then pass this integer index into our model for it to be embedded, which will be covered in more details later when we start to write our code. Then this encoder generates one new hidden state using the current source word embedding and all the previous information. And it does this at each step. So finally, we take this last hidden state and copy it as the initial hidden state of our decoder. And along with the first embedded input of the target word, which is usually the start of sentence token that tells the decoder that it's time to start decoding, a new hidden state is generated. Then this goes through a fully connected layer and a softmax function to become our prediction for the first translated word. So this vector in magenta color is actually not an embedding. It actually represents the index of the predict word with the index of the highest value in this vector. In other words, the index of the highest value in this vector corresponds to the index of the word in our target vocabulary. And we just look into our target vocabulary with this index to find the word. Then we throw this newly predicted word into our next step along with our last hidden state to get our new hidden states and our new prediction of our next word. And turn by turn, it generates all the words that should be predicted. And finally, it gets onto this end of sentence token, which marks the end of its task, and our prediction is done. So what's the shortcoming of this model? The main shortcoming is that RNNs tends to forget the previous informations when it gets to a very late state. And the longer the sequence you're encoding and decoding, the more previous information it will tend to lost. And another drawback is that even if you are using GRUs or LSTMs, when you are in the decoding process, for each target word to be decoded, it actually does not have a straightforward intuition that tells it how much each word in the source sentence corresponds to the current word in the target sentence. And this will lead to inaccurate predictions. So this brings us to the introduction of the attention mechanism. And here let's look at our encoder block. So these are the hidden states one by one. And the concatenation of all these hidden states is called the output, which we denote with the word out subscript encoder here. And I just want to mention that if you have multiple RNNs stacked together, let's say if you have another stack here, the output tensor will be the concatenation of all the hidden states of the last stack. So yeah, you take this output tensor and you take the transpose of this decoder hidden state and you multiply them together, then apply the softmax function, you will get what's called the attention vector. So what does this really mean? This actually represents how much this hidden state of the decoder is related to each of the hidden states in the encoder. And then you take this attention vector and do a matrix multiplication with the transpose of this output tensor. You will get what's called the context vector. And this basically represents a weighted sum of all the hidden states in your encoder based on the values in the attention. So yeah, now let's go back to our sequence-to-sequence model, but this time with attentions included. So here again, you have the first hidden state of the decoder, which is a copy of the final hidden state of the encoder. And along with the concatenation of the embedding of the first target word, which is the start of sentence token, and the context vector that we have just derived, you'll get the new hidden state of the decoder. And again, you do a fully connected layer followed by a softmax to get this output vector. Then similarly, you take this newly predicted word here and concatenate it with the new context vector. I want to mention that this one is newly computed with the newest hidden state and all the encoder hidden states. Yeah, and you get the next hidden state and next word. And one by one, you get to the end of the sentence. So this time, when you are predicting each word, you will know that how much attention you want to pay to each word in the source sentence. and this will greatly improve the performance. Now let's start coding. As you can see here, I have a separate script for preparing and processing the data files so that we can generate the data files that we can use in the future. Here we have downloaded the UniDecode package here. This one just removes all the unwanted tokens as well as transfer some characters in other languages into the corresponding ones in English. And here we have written a function to intake a sentence. I mean, this is the raw sentence from our dataset, and it will output a list of words that have already been cleaned. So here we are showing an example here. That's how it works, and puts the end of sentence token if we want. I'd like to clear things a little bit here. So everyone knows that we are going to use word embeddings in our models, but how are the words and embeddings related in our code? So we will need something in between called word indices. These indices are just integer numbers that uniquely matches to each word in your language's vocabulary for each language. So these indices are completely arbitrary. There's no special order to follow. As long as your indices are unique and your words are unique for each language, it will work out the same way. A tip is that we want to assign 3 of the word tokens with no indices, including the padding, start of sentence, and the end of sentence, which I will say 0, 1, and 2 respectively. Of course, you can use any number else as long as you know it, because we are going to need them later. But it's a better way to keep track of them by using 0, 1, and 2. And in our encoder, we are passing in word indices, which will then be converted into embeddings in the model. Then finally, the decoder is also outputting indices corresponding to the words in the another language, so that we can find the translated words in the vocabulary of the other language. The key point is that once you have trained your model, you do not want to lose the word indices that you have used or have them tampered in anyway, or your model will become useless. So here's our function to clean our data and prepare them in the text files that enables us to directly use them later. We run this function once, and it will permanently create the training and testing files, as well as the word indices for our each language, and store them in our workspace. So that's how I prevent data leakage and prohibits the risk of messing up our word indices. Also, it will make the data loading much quicker in our later stages, because these works won't need to be repeated every time we open our notebook. So as you see, here I have set the maximum lengths for English and French to 10, and anything beyond this are discarded. That's because I don't have a dozen of A100 GPUs. All I have is a Colab Pro subscription that provides a limited GPU resource. We are going to restrict our model's complexity also, and correspondingly we will need to restrict our dataset. So I think this is a sweet point. And we run this whole script all in once, so that it will create the files needed. So it creates these 4 files based on this one file that I have just downloaded. And these are originally we have a size of more than 130,000 for the whole dataset, and after cleaning, we have about 90,000 for training and validation, and the remaining about 1,700 for test. So I will download these 4 files as well as the source file, and show you how they look like. Training dataset has the same format, but it's a subset. It's a subset, right? And we have selected the ones that meet our length requirements. And this test set, similarly, is also a subset of the downloaded version. And here are our lookup tables for the word indices. This one is the French one. So these are basically 2 lines. The first line stores the unique indices. We have these many indices. And the second line stores the corresponding unique words. And same way for the English index lookup table. Okay. So for all our future works, including further data processing, model developing, and training and testing, we are going to shift to our another script here. So here we again have this sentence toward list function, and this part of the code actually reads the CSV files that we have just created to store the indices for words, and uses some functions to make our lives easier. I will show you how the functions work. So let's say words to int. Let's do hello word and period, and not to forget our end of sentence token. Yeah, it's returning the indices. And let's try French. Bonjour. And monde with period, and do French. Yeah, also a list of integers is returned. Now let's try into words. Let's see range 0 to, let's say 10. Yeah. And also English. Yeah, so this is straightforward. This is basically how it works to transfer between words and indices for each language. Now let's delete this. And this part is our code for loading the training and validation datasets. So what this basically does is that it reads the dataset file that we have just created and turns the sentences into indices, then puts them into Pytorch integer tensors. Also, it will pad any sentence that's shorter than the max length to the max length with zeros. Why we need paddings? That's because we have used the attention mechanism that will need a constant length for our encoder hidden states. So we must use zeros to add any input into the same length. And here we have a train and validation ratio of 92 to 8. We don't need any test set here because we already have our separate test file. Here we have sorted the training set by the length of our target language, which is English. I did this because this will save our some computing time, because we are using batches when we are training. Let's imagine that if you have samples with varying lengths in your batch, because we are feeding the decoder word by word, and when in a batch that's actually column by column, you will have to feed the columns until you reach the very end of the longest sentence. And for many of the times, you are feeding zeros because your shorter sentences have already ended. So that's not very efficient. And the way to tackle this is to put shorter sentences together and longer sentences together by sorting. So for the batches with shorter ones, you will reach a column that's full of zeros, meaning that all the sentences have ended. Then you can quit the training loop, which saves the running time. However, what we must remember to do is that we must to do inter-batch shuffles when training. If you don't shuffle the batches, your model will likely be biased to predict only long sentences or short sentences, depending on the direction you have sorted your dataset. So this is very important, and we will get deeper into that when we are writing the training code. And here, just let's do some explorations for our datasets. Let's see. Let's just have some brief look. Yeah, so these are all shorter ones, and all the remaining spaces are padded with zeros. You can actually use other integers, but it's just more convenient to use zeros here. And what I meant to save the training time when you are feeding the target words into the decoder is that when you are reaching this column, you see it's all zeros, so that you can just quit your training loop here. And all the remaining columns can just be forgotten. And let's go to the end of the dataset. Yeah, so these are the longer ones, longest ones actually. So let's delete this.